Okay, here we go. So this first question, this is a very typical question in the exam. It could be 4 marks, it might even be 5 or 6 marks. So we need to get the details. So we need to talk about diffraction. We need to talk about the distance travelled. So they meet in phase. Where they meet in phase, we get constructive interference, we get a bright fringe. Where we get 0.5 of a wavelength, or in fact 1.5, 2.5, 3.5. So we could write this as n plus 0.5 lambda. We get the waves meeting 180 degrees out of phase, so we get destructive interference, which is a dark fringe. So lots of detail required there. Question 2 is the basic calculation. So as always, write the formula, substitute the numbers, make sure you get the units correct. So very often they'll give you millimeters and centimeters. So the slit separation 1 millimeter, 1 10 to the minus 3, multiplied by the fringe separation 0.15 centimeters, divided by 100, divided by 2.4 meters. You would expect normally to get a value somewhere between 400 nanometers and 700 nanometers. Not necessarily, because this does work with UV and infrared and indeed any of the wavelengths in the electromagnetic spectrum. But generally speaking, we would expect to see visible lights being used in this. Also, we need to consider what would happen if we make certain changes. So very often the exam question might say, if you reduce the slit separation. Now this is a good idea. The reason why is because reducing the slit separation A would increase the fringe separation Y. And we can make reference to this formula here, because the slit to screen distance in part A doesn't change. The wavelength certainly doesn't change. So if I reduce A, if I make that smaller, in order for both sides to balance, I'd have to increase the delta Y, which is what happens. So your explanation could make reference to this formula here. So it's a good idea to keep A as small as possible, because that gives you a larger fringe separation, which is easier to measure. Similarly, if we increase the slit to screen distance, that is making capital D larger. Again, lambda's the same, A is the same. If I make D larger, I'd have to make the fringe separation Y larger in order for this formula still to make sense. And again, this is a good idea in practice to increase D to make the fringe separation as large as possible, to make it easier to measure. And we could also say to reduce the percentage uncertainty.